So, good evening, everyone. So, we would like to start this session now. And for your information, this whole session would be uh, recorded. And to start off the event, I would like to give a small formal introduction about our community. So, AI ML Nepal, where through this community, we're trying to create this network of all the AI and AI/ML practitioners uh, revolving around Nepal, so that we can create a pool where people can actually communicate and work on their ideas together and share their knowledge. And So yeah, please keep getting engaged in our community Slack channel where we have a lot of talented working professionals there too. It is a great platform to get linked up with people that are already a, that have already started their career. And yeah, so with that, I would like to introduce our I would like to introduce Sijan Bhandari. He will be delivering the uh, talk for today. So hello, Sijan. You can take over now. You can start with
Yeah.
a small introduction about yourself and you can get
Mhm.
going.
Okay, let me share my screen first. Give me a minute. Are you able to see my screen?
Yeah, yeah.
Okay, perfect. Okay. Hi everyone. I am Sijan Bhandari. I currently I'm located in Germany. I have recently started my machine learning journey from one of the startup company here in Germany. Before that, I worked as a software engineer for almost 5 6 years in my own venture on my startup, and then I couple of years also in part of software development in Leapfrog technology. While working in couple of projects there, I was I got some ideas how to enroll myself into data science uh, because at that time I was attending some of the sessions outside and I got to know about the tools and technology, but it was really hard to follow what is happening underneath, and that was one of the change in my decision to join as a master here in one of the technical university. Once I finished my master, it's been already 5 months, and then I joined this my first as a machine learning engineer. That's all from my side. If you have any questions, if you want to ask in between, please you can ask anytime. Now
So
let's
yeah,
start.
Susan,
Yeah.
before you get started, like I would like to say a
Yes,
few
sir.
words, like regarding how this event will go on. Like, Susan will be delivering the whole presentation, and in between, anyone can ask questions, but not by turning on their mics, but rather you can type in your questions in the chat, and after some questions accumulate, I can stop Susan and I can uh, give him your questions, and we can have sort of engaging talk kind of event. So just so that it gets more engaging for everyone. So yeah, please drop in your questions right away when you have them, and we can do that. Yeah. So Susan, please, you can start.
Yes. Yeah. Thank you very much, Ivan. Before starting, I would also like to thank Ceci Dai and also Min, who has been Ceci Dai, especially he was the person who connected me to this event, and also Min, he has helped me to understand about the event, how the previous events was happened. I went through the website also. It looks very nice. I think I missed a couple of events, but I hope in the future I'll be the part of the community in coming days. Okay, let's start. So the today's topic is neural architecture source. Um, I'm making this session as basic as possible because there are so many topics to touch, and 45 minutes is not enough to for me to make you all understand all the concepts. So what I do is I will try to make it basic, and in future, if we think it may be helpful to make it more technical, we can go in a very detailed level with understanding of the computation algorithm and everything. Yeah. So let's start. Um, First thing, I think we have been gone through so many research papers. We have been using so many existing neural networks to solve the problem in our daily life. For example, when it comes to image domain, there has been so many research. Every couple of months, they come up with the new neural networks. But if you invest a couple of hours in the paper, they always have this idea why they come up with these new changes. Yeah. For example, let's start with the AlexNet. I would say it's one of the early neural network. I'm looking at the bottom here, the AlexNet. It has a very minimal design to solve the image classification problem, I would say, because it has simple convolutional neural network and a couple of pooling layers in between, and it did really great job. And it also, I think, one of the good neural network at that time. But during the couple of years, people come with new ideas. For example, in between, here is one ResNet, uh, which has around 70% top one accuracy. And when it comes to more, you can see the exception and inception over here at the top, around 80% top one accuracy. When we do look into these architectures, we usually see that, okay, they have these new components, but we never see why they come up with those new components. Yeah. For example, the residual neural network, if you look closely, they have this intuition that having a residual network can somehow impact the learning process high. I think it's very much related to human learning process also, because some of the time in the future, if we learn something today, after 10 days we sometimes forget some of the aspects. Why it's happened? Because we don't learn the same thing every day. Maybe the consistency is kind of the problem. Yeah. At the same time, if you see the ResNet design, they have this residual block. Why they design it? Because they want to make sure some of the input from the very last part of the neural network can be forwarded at the front. So the training process can learn some of the knowledge from the previous layers, and they can, not in the sequential fashion, but that there can be some sequential other residual network that can map previous knowledge at the front. So this kind of design has a very much impact on how human learning also works. Yeah. Similarly, there has some changes on the inception model. Briefly to mention, they have come up with the idea, for example, how to use parallel knowledge transfer in between the model. So they have like multiple filters, one of the model, and they use these multiple filters to parallelly learn some portion of the images at the same time. Yeah, and this kind of changes is very much related to how human learn, or any other animals learn. But how to come up with these things? It's very tedious, isn't it? So now, when it comes to designing the optimal neural network for your problem, it seems like you have to understand some how learning it actually happens. For example, skip network, some residual network, I don't know, maybe using multiple parallel learning at the same time within the network. So these are the very much learning frameworks for humans or other animals. Yeah. How to use those knowledge to reflect into designing an optimal neural network? That can be a very hard problem if we see. But at the same time, there has been this paradox. You can see we say that we have a large number of data, I think we can use neural network. That's how people starts. If we have like thousands, millions of images, we say we should not use this very generic machine learning or traditional machine learning models. Let's use neural network because we have large data. But we never discuss much about what the architecture should like, what the design should like. Yeah. And also, if you look closely on this particular figure, I have two different columns, the left and right. Why I split them? Because the left side is very common and very generic, that also comes into our traditional machine learning models, like the concept of regularization, the learning rate, batch sizes, epochs. It can be because even you can use um, gradient descent to solve a linear regression problem, right? So you can use this concept of epochs, batch learning, and everything in the while solving the linear regression problem. So why I split it? Because these parameters on the left can be has been optimized for a long time using other frameworks also. But when it comes to neural network, they have very specific requirement on the right side, like whether I should use fully connected layer, CNN, pooling, LSTM. I don't know. They have so many options now. How many layers should I use? How many neurons per layer should I use? Should I have only one 3 by 3 filters, or there can be multiple? Yeah, not number of filters, and the last one is the filter size. What should be the size of the filters? So these kind of decisions has been very hard, you have to be very proper to make your neural network optimal for your problem also. Now, when it comes to the design guidelines, I think it's really hard. As I mentioned, I think I'm focusing on the hard part very much, because we never know, because we usually start with the basic standard. There is no any gold standard, but we say let's start with the very basic neural network and we'll evolve. Yeah, we do some hit and trial. We think of what kind of activation functions, maybe change, maybe start with the 10h and I would go to the ReLU. There are some design decisions why to use those activation functions. Also, you have to be very clear how many hidden layers. Let me start with the small number of hidden layers. I don't want to start with the 10 hidden layers because it sounds very complex to me. Yes. And then I will also, everyone will do the same. We evaluate some validation performance, and then we'll see, okay, it's doing better. But it's kind of a very much rough hit and trial. It looks like you have a very large set of parameters you need to be go through. Yeah, you need to go through. But at the same time, there is another approach using automatic approach, the second one, where we can rely totally on using automatic machine learning. It can do most of the part by itself. It sounds very easy to say it can do everything for you, but it's not. So the outline, that was the kind of motivation I was trying to bring, but the outline would be somehow the overview of these very broad and the jargons, automatic machine learning, neural architecture search, and the reinforcement learning. Secondly, I will tell how reinforcement learning fit into the neural architecture search paradigm. Yeah, and then we will look into how reinforcement learning actually solve the problem. What are these terms like? What is actually happening inside the algorithm? But I will try not to put computational part, but I will try to make it more clear in terms of visuals. On fifth, I will give one small demo where I'll try to explain how we can use a reinforcement learning agent to solve a 2D parameter space problem. This is not a problem. This is like how we can use a simple reinforcement learning agent to find optimal parameters for, let's say, linear regression. Yeah, so that can be a starting point. And then I will conclude with some major points. So let's get the big picture about AutoML. There is a very thin line how people put automatic machine learning, whether which components should be there, whether which some components should not be there. It's a huge discussion. But when it comes to my mind, I usually follow what can be automated. And these are the 7th different things that can be actually automated within machine learning. Data preprocessing, yes. Feature engineering, because it's really hard. which features are good. Maybe we can have some derived features, feature selection. There are so many approaches for feature selections. Yeah, that can also be automated. Hyperparameter optimization, yes, there are so many hyperparameters that we already discussed in the previous page. Training and modeling, this is also one of the part where it's basically a loop, but it can be very tedious also. And the analysis of the results, where some of the part, for example, whether the model is good enough or bad enough, that can also be automated in terms of performance, in terms of some other evaluation metrics. But when I preparing this slide, I put this neural architecture search just in between, because the neural architecture search only comes when you are using neural architecture. But AutoML is also designed for the basic or the generalized machine learning models also. It's not only for the neural architecture. Yeah. Now, there can be a confusion how neural architecture search is different from the hyperparameter optimization. Like we discussed earlier, hyperparameter optimization is looking for the hyperparameters. It can be anything. For neural network, even the layers, neurons are the hyperparameter. But when we talk about the neural architecture search, we are just talking about the architectures, exactly the number of layers, what kind of cells, what kind of connections. Those are the actual architectures that define new neural architecture. Now let's go to the neural architecture search. Um, we just found that neural architecture search is a part of whole AutoML, but neural architecture search itself has a very different pipeline. You have to think of how to define the search space for your problem. Let's say you are trying to solve some image classification problem, and then you saw there are so many options. There are so many layers to think of. FC's fully connected layers, CNN. Could be max pooling. There could be skip connections that might be helpful. So those kind of layers or units, and how many of those neurons, maybe there could be a concept of dropouts. Let's add some dropouts in between, or the filters and the kernel size. So you can see the search space can be as large as possible with the knowledge you have. You can add as much on into it. And the second one would be searching strategy. Now, what should I use to find this? How should I navigate in the search space? Whether I should use simple grid search? Well, we can. It has been used. People have been using it, grid search or random search, for most of the time in a benchmarking, because they want to see our new algorithms can still outperform the baseline. Yeah. So grid search and random search are still there. It has been using in most of the papers if you see closely. That there is a Bayesian approach, the genetic algorithm, darts, and RL. So these are the common strategies you will see when it comes to neural architecture search, and which one to use. There are so many options like presented in here, but we will be focusing on reinforcement learning and how it can be fit into this thing. And finally, we have this performance evaluation. So in this particular loop, you can see that whatever the strategy you use, that strategy will generate some sample architecture for you. It should go through some evaluation process. The evaluation gives some performance metric, and that performance metric is a kind of a hint for your searching strategy, which direction to move in your search space, whether I should go up or down. I don't know, and just up and down doesn't make sense, because this search space is a very multi-dimensional parameter space. Yeah, it can help. This performance metric will help you to navigate in your search space in one way or other. That's the overview of neural architecture search. Now let's go to the reinforcement learning. I think most of us have already heard about it. We have seen about some of the things. We have some really interesting research happening, mostly in the Berkeley lab, the robotic department. They designed some walking dog based on reinforcement learning. Yes, so it's very much exciting. But we have to know the very fundamental basics for this particular session. In reinforcement learning, we have measure two interactions. I would say the interaction components, the agent and the environment. The agent is someone who is in the environment doing some hit and trial. So he is a kind of a baby. He want to learn how to step up and walk, but how he do? He try to fall all the time, and then by falling, he also some acquired the knowledge how he put your knee position, how to should he put your body position so that he can stay up for a longer time. Yeah, so how baby learns. This is the exact scenario it happened in most of the learning if you use reinforcement learning process. Let's start with the simpler example. I want to design a recommendation system. Now, what is my agent? My agent is a recommendation system. I want to recommend some, let's say, videos for my website to new customers. And what is the action my recommendation system will do? It will recommend 5 videos, let's say, when you are logged in. That is the action my recommender system do. And what is the environment here? The environment is where my agent lies. So the environment is, it's a very abstract term in this learning, because it poses all the things. Yeah, it can be very partial environment, it can be fully seen environment to the agent, but most of the time it's a partial environment where agent try to acquire knowledge about how to perform. In our case, I would say the environment itself is our platform, and the state, the observations are our customers. Let's say in recommendation system that we just described, if you want to recommend a video, what you need some knowledge about your customer, right? So the knowledge about the customer is your state, is your observation. You recommend 5 videos, and then your customer stay, let's say, 1 hour in one video, then that's a good reward. Yeah, because you suggested something, and then your customer stay for 1 hour, or the customer clicked your event, he liked your clicked your video, liked your video, then you are getting more reward. So that means your agent, your algorithm is doing really good. So this is a feedback loop. Once the customer do something with the recommendations list, then your system will get some reward, and he will think that, okay, I'm performing good, I'm in a good direction. Within the 5 videos, let's say customer spent 1 hour in one videos, but he didn't spend any time in other 4 videos. That also means agent will learn, I should recommend more videos related to video one, not other 4 videos. Yeah, so this is the learning process. It happens not in a single time, but it's a continuously in a sequential manner. But when it comes to reinforcement learning inside the neural architecture search, it's the same thing. Only difference is our agent is agent is a controller now. What it does is it will, based on the search space, it will sample some architecture. That architecture is a child architecture which goes through some training process, and we will get some validation accuracy as a reward back to the agent. So you see, it's the same framework. We have the recommender system. It gives some reward when customer behave on the system. Similarly, we have this sample architecture which trained itself. Will train this architecture with some data. We'll get some validation accuracy, which is the reward for the controller, and it will think, okay, this particular sample architecture is doing much better, I should follow on that direction, I should navigate with the architectures on that direction. Maybe having 2 layers is much more sense because I'm getting more validation accuracy, or having 2 convolution layers in between makes more sense to me, I should go on that direction. So this is how the whole loop look like. In every time it will learn, and it's a very exhaustive process because it has to see through all possible until it goes to the optimal. When I say it has to go through all, it's not like a grid search. What I'm saying is it has to know basic knowledge of how the environment looks like. Otherwise, it won't be able to understand which direction to move. Yeah. Now let's go a little bit deeper on how this reinforcement agent look like. I mean, we talked about this agent guy here, this agent guy here, but what is the agent itself? Agent is nothing. It's abstract term. Agent is abstract term because it has been fed or it has been designed as a reinforcement learning algorithm. Because when we say I have an agent, recommender agent, it's not actually an agent, it's an algorithm inside. Yeah. So we usually use the term q learning agent or policy gradient agent. There can be any different kind of reinforcement learning algorithms you can refer to. And what is learning? It's actually learning a policy. Yeah. So in a high level, the agent just receives the observations and the reward to learn optimal policy with the help of reinforcement learning algorithm. Yeah. So what we are trying to learn at the end, the output, the product of the whole system is a policy. So policy is our final output that we are trying to learn, and that policy is related to our agent. And how the policy is motivated, like we discussed already, policy is motivated by the idea how to get more reward. So you can see here, our policy, which is inside our agent, is more motivated if we give more validation accuracy, good validation accuracy. Then he will say, okay, I think this direction is good enough. Yeah. So it's motivated towards maximizing the long-term rewards, not just it says this particular design I have 92% validation accuracy, I'm fixed, this is the best. No, it won't do that. It will say, it will try to evaluate for a longer period of time. It will say I will stay, let's say, 10 more episode and I'll decide. So it can be framed that way. Yeah. It will try to have long-term vision. It's not like just getting one and then settle down. And the third term is, it's nothing much, but it's a simply can be a very small lookup table where, given these combinations of parameters, please generate this neural network, like a very simple lookup table. Or it can be a very sophisticated neural network. What it do is, we will give some strings of some strings structure of neural networks. It will design some neural network, train the model, and estimate the validation accuracy, and then it try to learn the parameters where to move around. Yeah. So it can be very simple lookup table, or it can be very sophisticated neural network. Now it gets a little bit messy here.
Season, I had a short question before you move forward.
Yeah. So,
So like uh, this all seems to be very computationally heavy,
mhm.
and it just like from what I've understood till now, it just seems like a trial and error thing, and it takes a lot of computational space. What do you
Mhm.
think about it?
Yes, that's very true. Yes, it has been also the major trade-off on these things are, for example, whether we want to have very new architectures, because most of the time when we design new architectures, it's a human biased. We use our previous knowledge and then we introduce the human bias to design these things. But if we don't want to introduce human bias into our neural architectures, we have to use a very large space and we should let it run for a couple of days, I don't know, right? But at the same time, it's computationally very heavy. Yes, you are right, because there are so many possibilities of combinations, and then that's a trade-off one has to deal with. Maybe we can talk later at the end how people are trying to resolve this issue, but that's a very valid question. Yes.
Sure.
Mhm. Okay, so let's go back. So now we know how agent look like. Agent is a just it has some policy which is trying to learn from the environment, yeah, based on some observations and reward. This looks more math. I won't try to go in much detail, but we can do at the end if you want to. But what is happening here is I will try to give some idea what it actually look like. Yeah. So this is nothing, is a policy, our policy, the whole thing on the please don't look on this those two measure plus sign. After this, the what is happening is just optimization of this particular log of probability distribution function. Yeah. So our policy is P, which has corresponding parameters theta, and we are trying to optimize theta based on the validation accuracy we get in every loop. That's it. That's all it's happening here. You don't need to worry about these two things. If you want to, you can go through the reference in the slide. It's one of the first paper they published for using reinforcement learning for a NAS problem. basically here we can come back if you really want to discuss, but I just want to focus on the right side where the whole objective function is this policy which is learning based on the validation accuracy and is trying to optimize the parameter theta every time it has some decision to make. Yeah. Now let's see what is happening inside. Let's say in a first time we run our neural architecture search using some reinforcement learning. The first action, let's say our agent decided in a random, this is my first decision. He says I want to have a one fully connected layers, just take a fully connected layers, sorry there's a has to not be here, the number of layers I just want to put 2, and each layers I want to put, let's say 100 neurons. It doesn't look fair because sometimes the output layer should have the number of exact classes, but it's just an example. And I want to put some dropout maybe in between these layers. So this is the first action my reinforcement learning decided. And what will happen? This is simply a string generation, yeah, by my one of the network it does. And then based on this number of information, I will design a child network. So you can see I try to have 2 layers, maybe 1, 2. I have maybe 100 layers. I didn't put 100 neurons here. I mean, it's not possible, but I just put, it makes more sense if I, sorry, right away. Sorry for that. Maybe it could be more obvious if I put just 4 here and it looks more easier to see. Yeah, so I just decided I will just put 4 neurons, and you can see here the child network is designed based on these guys, whatever I gave, and then it goes through some training process. And once the training process happens, we have some reward for this particular part, and the reward is like the evaluation on validation or held out set, which is 92%. And this is my reward value now, because I'm getting for this particular architecture this amount of validation. It will go back and I will update my policy based on the whatever value I get for the reward. Yeah. So this loop happens so many times. We have some other constant, the outer constant, like how many episodes we want to learn, what are the threshold value, for example, whether it can go above 92, or those threshold are the outer level constant one can put as a design decisions, whether I will update the policy for only 1000 episodes, or I will let it explore or learn from more than 2-3 days. That can be a design decisions. This is one based on this algorithm. This is a very small algorithm that I worked during my research at the university also. Let me explain what is happening here. We have this small moving guy who is our agent, yeah, and then this 2D parameter space are the parameters that are the kind of hyperparameters. Let's say let's say if we are using linear regression problem, we have parameters theta1 and theta2, and I want my agent to find optimal theta1 and theta2 by going through this 2D parameter space. How I designed the 2D parameter space? Mostly the alpha and beta, let's say we have equation for linear regression, y is equal to alpha 1 times x times beta 1 something. Yeah. So those alpha 1 and beta 1 are they have a very much constant, because they have already defined what distribution they follow, because that's already a problem in linear regression. When you do those parameters supposed to follow most of the time normal distribution, maybe sometimes some beta distributions. Yeah, so we already know what are the scopes of those parameters, and you define, let's say I use theta 1 between 0 to 10, and then theta 2 can go from, let's say, minus 2 to minus 5, or I don't know, minus 2 to plus 5. Yeah. So those are the parameter space, and then you simply create your maze. It's simple grid, some simple grid where you will know how the my agent move around. Now, what are these colors means? The colors gives you kind of rewards. For example, what I mean by reward, if you know your parameter space, yeah, you can easily calculate some form of evaluation metric for how your algorithm can work. If you are using linear regression, you can use simply a RMSE, the root mean square value, and then use it as your reward function, reward value. Yeah, it's because higher the RMSE, I would say no, that's a very bad reason to go. Very less the RMSE value, that's a very good reason to go. So my agent will know based on the RMSE value which direction to move. Yeah, so you can create your parameter space the way you want. It's not just defining a simple evaluation metric like RMSE, but it can be anything the way you want. Maybe it can be, I want to design an algorithm to have lesser carbon footprint or lesser memory footprint. That can be your parameter also. You can design your parameter space based on your own idea. Once you know those things, those the constant of your parameter space, then you can simply start with small grid. It won't be possible if you have multiple parameters. Yeah, you have to come up with others. But once it has this information, then it can move around, like we discussed already. It will do some hit and trial. It try to explore. You can see that this agent guy, he's trying to go through some of the space even though he knows those things he doesn't should go, but he's going there because he do some random exploration also. That's one part I didn't explain. Reinforcement learning always work with two basic principles called exploration and exploitation. The exploration is the part where he has a random behavior. He want to randomly explore because he want to know whether I should use that particular direction or not. And exploitation is, since I already know this position has given me good value in the past, let me go on that direction. So this trade-off between exploration and exploitation is a very hard problem in reinforcement learning, because most of the time if we let our agent to explore more, they can come up with the new parameters, maybe new source points where our model can perform very well. But if we just put more emphasis on exploitation, they end up learning and will be a little bit biased towards the past knowledge. Yeah. Um, After that, I think I can simply go through the code, but let me conclude and then we can go if we have more time. Yeah. The conclusions. We got to know that automated machine learning can be used to automate end-to-end machine learning process. This is a definition I use. I already mentioned there are some thin line between how people are using it, but I would say most of the tasks that can be automated should be inside AutoML. We can also see neural architecture as one of the subfield inside automated machine learning. Third one, neural architecture search is a general setup to find an optimal neural network for a given problem. Yeah? So in general setup, why I mean by general setup? Because neural architecture solve problem can be used with so many other searching strategies, not just the neural network. Like we said, we can just simply use grid search for neural architecture. We can do that. We can use, let's say, evolution methods, evolutionary algorithm. And so it's a general setup to find optimal neural architecture, but strategy can be anything. The third one, it's a very interesting one. Reinforcement learning in neural architecture search finds an optimal policy. I would like to emphasize on the part optimal policy, okay? Because most of the time, if you use other strategies like grid search, random search, evolutionary algorithm, yeah, Bayesian optimization, you will end up just getting output as this is your optimal neural architecture. That's it. But when you use reinforcement learning, it won't give you just one architecture as a best optimal architecture, but it will give you a policy, a very much optimal policy. And I'm very much interested on this direction because finding the optimal policy is very interesting, because now you can use this optimal policy maybe optimize in other subfield, other different problem settings. You can maybe twist some of the thing and make it work for other architectures search, for maybe starting from image small domain problem to large domain image problem. Yeah, so it can be done with, if you have a really good policy that has learned so many things from your earlier setup. With this all conclusions, I would like to thank you. If you have any questions, let's discuss. Or if you want to go through this particular demo, I can share briefly what I did. Any questions in between?
So I had a question on the last conclusion point.
Yeah.
So is finding an optimal policy rather like, you
Hmm.
know, creating this model and then using it for fine tuning later on? Like, is
Hmm.
that optimal policy like a model that is trained on a large data set, which could later be fine tuned type of thing?
Um, yes and no. Yes, you're right. It can be tuned with other problem set. But what I mean by reuse part is, for example, let's say we have a setting of time series data. We would like to train our model. We would like to use a NAS with reinforcement learning to find optimal architecture for your e-commerce platform where you have a sales pattern. Yeah, so you have like customer behaviors of different sales pattern, and I want to find which neural network could be one which can predict really good sales every week. I don't know, every horizon of 1 month or something. But at the same time, you come up with the another data set which is also a time series. Yeah, but time series, but it's not a sales data, it's a very different data set. Then since we learn policy on the time series data, the time series data is a time series data, it's a standard protocol, because now policy is also aware of how to behave on this time series data. Then you can use those policy learned on the sales time series data to another domain of time series data, because it's kind of a similar domain the policy has been exposed to. Yeah, so that's how I mean by twisting part. Did you understand? Are
Yes.
you right? Yes. Okay.
Yeah.
Okay. Any more question?
Does anyone have more questions?
Please feel free to. Also, one thing I have to mention: I am not explaining as an expert in this field. I'm explaining the way I researched in the past. So there could be some mistakes. I would be happy if you point out something or you want to discuss something. That will be very interesting to know. Also.
So actually, I had another question. Like, what is the actual benefit of using reinforcement learning on a neural architecture search problem?
That's a very good question. Yes, the benefit. Yeah. So this. There has been a very much discussion about the benefit of reinforcement learning itself. One benefit I have been highlighting in this conclusion, the fourth one, we are not just outputting a single neural architecture for your problem. We are outputting the whole policy, and it's, I have to highlight it because policy is not a simple thing. It's a very sophisticated neural network. It has understood your problem for a long while you train it. Yeah. So now having this policy is a big deal, and then you can explore how you can change it to other field. Just to give you a hint, now there is a new trend on meta learning where they want to learn different tasks, and then they are trying to use this policy mechanism of reinforcement learning to transfer knowledge from one task to another task in meta learning. Yeah, so these things is only possible if you have designed your formulation in terms of some neural network. If you parameterize it, because neural network itself, we have so many parameters. It's learning so many things within these parameters that can be evolved into a new solution for a new kind of problem, which is not possible if you just think of using, let's say, random source for neural architecture search. Because random source, what it does, it will go through random search, it will find the architecture, and it will just give you one architecture and says, okay, this is the one you can work with, which is, it's good. It's good because if you want to just one architecture, but it's not good if you want to extend your finding to another problems, or you want to extend further to solve similar problems, because it has been a problem of data set. Because if you have to jump from one problem to another, you won't have all the data set required to solve all the problems, and then you end up using transfer knowledge, transfer learning, or making so many data augmentation is itself a good. But if you have some neural network which can be twisted a little bit and learn, that would be very interesting to have, in my opinion. Okay, and also I think some of us also are interested, but very much shy to ask questions. If you are really interested, please you can contact me on LinkedIn anytime. If you have any questions, we can have a many different one-to-one session. I'm up for it. And if I have any other resources to share, I'll share in the our Slack channel definitely, and then we can also chat there.
So yeah, do we have any more questions from the audience? I guess not. Uh, so I think that we've come to the end of our session. Thank you, Season, for this wonderful and informative session. And as per Season, anybody can please contact him and talk to him about the subject and learn more and discuss more. And um, again, we would love to be the platform for people to discuss so that more people get to learn from your own discussion. So please post your queries, thoughts, discussions on our Slack channel so that we all learn together. And thank you everyone for attending the session. It was a great one. Thank you, Season, again. I really loved it and it was really informative for me. And I hope it was for everyone else too. Thank you.
Thank you. Bye.
Bye bye.